All right, let's do a quick review on oxidation states and how to figure them out. Oxidation states are basically the charge on an individual atom, and it's important for us to identify these so we can understand how oxidation reduction reactions take place. There's some arbitrary rules, at least it feels like it, when we are trying to understand and come up with these oxidation states, these charges. Rule number one, when we're looking at an element or a compound, if it's just the element of itself, it will have an oxidation number of 0. No matter what the subscript is, um, the individual oxidation state will be 0. So here are some examples: zinc, oxygen, iodine, and sulfur all will have oxidation state of 0. There's no charge listed, and we can assume that it's 0. Secondly, if there is a charge shown, then the oxidation state is just the charge. Pretty simple. Thirdly, and probably one of the most important rules that we're going to be using, is oxygen most of the time can be assigned a charge of -2. It is very electronegative, and so it'll pull electrons, and it's kind of one of the more stable anions out there. So oxygen at -2. Few exceptions, which I'll say right now and go over in a little bit. There's peroxides and superoxides that oxygen will not be at -2. Those are fairly rare, and there's some well-known examples you should be aware of, like hydrogen peroxide. Here, oxygen will be -1. Secondly, to help figure out a lot of unknown oxidation states, it's important to assume hydrogen will be +1. And that's not too strange to figure out because it has one electron it can give up. There is a rare situation where hydrogen will accept an electron and become -1. And that's with group 1 metals. Okay. It's important to understand that the overall charge of a compound is the sum of all the individual oxidation states, and according to the number of elements there are in that compound. So let's practice a few of them. So these are some important ones that we'd like you to be able to figure out the individual oxidation state on each element. And I'm going to go through a couple of them in detail, and then you can practice the rest of them. Okay, so here's an example of potassium, and it is +1. Oxygen we would assume is -2, and chromium is +6. Where do we get those numbers from? I'm going to jump to this next slide right here and help you understand how we figured out that for potassium dichromate. By assigning oxygen to -2, this is very helpful. We're going to also assume potassium +1. These group 1 and group 2 metal ions will often be their charge that they are in accordance to their column that they're part of, the group that they're in. So those group 1 metals will just lose an electron and become +1. Group 2s will become +2. So you can pretty much assume that those are going to be the charges there. The only thing we don't know in this particular one is chromium, and that makes sense because transition elements, they can really change their oxidation state. They can vary. So create a little formula. I have 2 potassiums at +1 plus 2 chromiums, which I don't know the charge of, plus 7 oxygens, which are at -2. And this is a neutral compound, and so I set it equal to 0. Solve for x, rearranging the equation, you can see that I can end up getting x equal to 6. I like to write the oxidation states right above each of the elements. It's important that we write the individual oxidation state of one of the elements. Some students will be confused and write a +2 above the potassium, and that's the wrong thing. It will lead to confusion later on. So we just want to know what the oxidation state is of one element. Let me practice another one that has a charge. Here's the carbonate ion. And what is the charge on each element? Well, oxygen we can right away assume is -2. Not because we see the -2 there, but because of the assumption that we made in an earlier slide. Let's set carbon equal to x, since I'm not quite sure what it could be. +4, -4 are some common ones. So I set x plus 3 times -2. 3 is the subscript from oxygen, -2 is its charge, and it's going to equal -2 overall because of the charge of the ion that's there, the -2 in the CO3 2-. Solve for x, and you'll find that x is equal to 4, and that is the oxidation state of carbon. So it would be good to go back and look at all of these other ones that we had in this list. And so we did the first two here, and here's some other ones. Once again, it's good to assume oxygen's -2 in these. I would assume in potassium pentachloride that the chloride's -1. And then I would assume fluorine is -1 in the sulfur tetrafluoride. So those are some good ones to look at. All right. Our goal is to figure out the charge or the oxidation state on each individual element. There's some exceptions or oddballs, as I mentioned. Hydrogen peroxide is one of them, where hydrogen's +1 and oxygen's -1. There is sodium peroxide, and it's a +1 and a -1 as well there for sodium and oxygen. There is sodium superoxide, where sodium's +1 and oxygen's at a -0.5. Crazy, I know. There is oxygen difluoride, where the oxygen is actually +2 and fluorine's -1. And this is because the most electronegative element rules. If you want to learn more about peroxides and superoxides, I suggest you search those words on Wikipedia or Google. And typically, we get these oddballs because these compounds are very reactive. But they're made from oxygen, O2, very reactive, sodium, elemental sodium, and potassium in these elements are very reactive. So you end up with some unusual and they're unstable compounds. All of this is important because if we need to, why do we need this? We need to use this to assign oxidation states to see who gets oxidized and who gets reduced in a chemical reaction. Here's an example of, here's aluminum plus 3 copper ions to give us 2 aluminum ions and 3 coppers. And the reason why we need to do those oxidation states is we need to assign those here. And because we need to know who is being oxidized and who is being reduced. So in this particular example, aluminum is a 0 on the reactant side going to a +3 on the product side. We ignore the coefficients. We want to look exactly at the elements themselves. And the way that aluminum switched from aluminum to aluminum +3 is that it gave off 3 electrons. Now, there's a lot of different ways to say this. We may say losing electrons or giving off electrons or donating electrons or producing electrons or transferring electrons or just simply oxidizing. So the oxidation state of aluminum is increasing in this reaction. This is called oxidation, or we say aluminum is being oxidized. Now the wording, because this is what scientists will do, we say, hey, go get me a reducing agent. And the reducing agent is the element, includes the element that's being reduced. So the reducing agent is the whole compound. All right, and a little way to remember this is that the element that is losing electrons is being oxidized, Leo. Okay, and then there is another element in this chemical reaction that is being reduced. It is gaining electrons, and that's the copper +2 ion. And we say that it is gaining electrons, or it's receiving electrons, it's accepting or using up electrons, or simply it is reducing. And so its oxidation state's going from a +2 to a 0 by accepting these electrons. And we say it's reduced, and copper +2 is the oxidizing agent. So we like to say what element is being oxidized or reduced, and then we say the whole ion or compound is the agent, in this case the oxidizing agent in this half reaction. So if you're gaining electrons, you're being reduced, call that GER. So you can remember Leo, Rohr's, GER. Now here's a few practice problems for you to look at. You can pause the screen here, your video, and look and see if you can identify the oxidation states of each of the elements in these 3 different chemical reactions, and then also who are the oxidizing and reducing agents. All right, hopefully you had a chance to look at those. Turns out that, let's put these all up, that as you assign the oxidation states, you will find that the middle one there, listed as A, somehow they all get listed as A, is not a redox reaction. And it looks like it with all the charges that are there. But when you assign the oxidation states, you see that chromium is a +6 here, it stays a +6, and oxygen is always a -2, and hydrogens are always +1s. The first and third ones are oxidation and reduction reactions. You can see in the first one that zinc is going from 0 to +2, and the hydrogen goes from +1 to 0. There has to be an oxidation and a reduction. Now the last one's a bit confusing. We'll go over that in just a second. So let's take a look at that first one real quick. Assigning the charges, once again, if it's an element in its standard state here, we just put 0, which is the case for zinc, and the hydrogen gas is the product. Hydrogen's +1, chloride's -1, zinc is +2, and -1 in the product there. So zinc's going from 0 to +2, therefore we say it's oxidizing. The half reaction is going to include the zinc and the zinc chloride compound, and zinc is undergoing oxidation, and zinc is also called the reducing agent. Hydrogen is going from +1 to 0, therefore it's reducing, and we can use the reactant and product in our half reaction to get us started there. Hydrogen is undergoing reduction, and we say then the whole compound HCl is the oxidizing agent. Once again, the agent is the name for the whole compound that includes the element undergoing oxidation reduction. Okay. A little quick note on setting up the half reactions. You need to focus on the element that is being oxidized or reduced, and we can kind of ignore the other element because it's a bit confusing, which is chlorine in both of those. More on that in other videos. The other oxidation reduction reaction is copper chloride. This one is unusual. We see copper is +1, -1 for chlorine, and the reactant side going to a +2 and -1 for the chlorine, copper and chlorine in the products, and then we see a copper showing up here. What's going on? Well, we see copper is a +1 going to a +2, and therefore it is oxidizing. And we would include the copper chloride going to copper 2 chloride plus an electron there if you were thinking about the half reaction. Copper is undergoing oxidation. That's the element, and then the whole compound that includes that element is the copper chloride. Notice I'm leaving out the 2 coefficient. You don't need to talk about that when we're using the names. Copper is also going from +1 to 0, therefore it is reducing. So it would look like this for the half reaction that we see copper chloride is going to copper metal. So copper is also undergoing reduction, and it is also the oxidizing agent. This is a rare example of a single compound being both the oxidizing and reducing reagent. So these are some important concepts to remember, and there's some very good videos out there on various other chemistry teachers, and I encourage you to go look at them. It helps to hear how to explain and understand these from different faculty members and scientists. So I wish you the best as you try to understand oxidation numbers and who's oxidizing and who is reducing. Thank you for joining me. I'm Dr. Ryan Hayes at Andrews University in the Chemistry and Biochemistry Department.